It's Mrs. Meehan, and in this lesson, I'm going to go over forces and how they relate to something called potential energy. So something that I'm going to go over in this lesson or this screencast is something called gravitational potential energy. So let's imagine a barbell for a moment. We'll say that its mass is m, and we're going to lift it vertically upwards at distance h by an outside force, so we can call that an applied force. How much work does that outside force do on the barbell? And this is similar to a problem we did at the end of the last lesson. But just to bring it back, we were actually getting to the concept of potential energy with that. So we know that work equals force times the parallel displacement. And since the acceleration in this example is 0, what ends up happening is the applied force is equal to mg. If you can recall from the last unit, let me fix my font there. We have acceleration equals 0, so the applied force is equal to mg. So it would be true to say that, even if you worked it out using the net force equation. We've done that a few times now. So we can take mg and we can replace that. We can substitute that in for force. So instead of work equals force times parallel displacement, you could say that work equals mg times parallel displacement. And in this case, since F and D are in the same direction, and we're saying that the parallel displacement D is a height, we'll replace it with a lowercase h there for height. What we're saying is that the work equals mgh. So this equation is just showing you pretty much the same thing of what we saw initially, but this is actually an equation for something called potential energy. And more specifically, gravitational potential energy is what we'll be calculating with this equation. So you could replace that. GPE is our abbreviation for gravitational potential energy. So the equation isn't actually that different from what we just used. We're just focusing on it as gravitational potential energy instead of just work. So let's take a look at an example here. So to the left, we have a person lifting a barbell. So hold on. Let me try to draw the forces here to help visualize. So he's lifting up this barbell, let's say. And so he's applying a force upward. Now, let's say this is at constant velocity, which means acceleration would equal 0. That means that the applied force is equal to mg. So we have, and I'll write it up here since that's not coming out too well. The applied force is equal to mg. Now we also know that he is raising this barbell up a certain height. So our displacement in this case is height. So going back to the work equation here, where work equals Fd, you could also say gravitational potential energy is similar because we're calling the force mg in this case. We're lifting something vertically upward. Displacement is h, so we have mgh. Now we know in general that the initial energy of a system plus work, which adds energy, would be equal to the final energy. So if our barbell had no energy to begin with, so that initial energy would equal 0, then work would just be equal to the final energy. But we just showed that we did work to lift the barbell. Work is equal to mgh. So this is what happened. Therefore, mgh is equal to the final energy. So if work is equal to mgh, and we just showed that mgh was happening over here, then we did do work in this example. And with that, we increase the energy. So, the barbell started down here, initial energy, and by the time it was up here, we now have our final energy is much larger. We increase the energy in the system by lifting it. Lifting it was work because work in this case is equal to mgh. So there would be a lot more energy up here once this is, let's say, above his head. And if he dropped it, it could be dangerous and hurt somebody since now it has more energy. So just to sum up this equation here, the name for this form of energy is gravitational potential energy, and we're just calling it GPE. These are not separate variables. It's just one thing. It just stands for gravitational potential energy. So that gravitational potential energy is equal to mass times gravity times the height. Essentially, it was derived from the work equation when you're lifting something vertically. Now, one important thing to note is that while changes in gravitational potential energy are important, their absolute value is not. So let's take a look here. When you're looking at some problems, you can pretty much define any height to be the zero for height. So no matter where something is in a question, you could just determine, it has an initial height somewhere, whether it's this last step of a ladder or the floor. So you could define that as zero, and that would end up, with GPE equaling zero. So let's say we look down here at the bottom here, gravitational potential energy would be equal to zero because mgh, in this case, h is 0 meters, would end up being zero. So whichever height you choose to call zero, changes in heights will result in changes of gravitational potential energy. For example, the floor level can be considered zero energy, or the ladder level can be considered zero energy. But if we're lifting something from this first step up to the handle, you would increase the gravitational potential energy, since now you'll have a change in height. Same thing down here, doesn't matter, down here we'll have 0 to 0.5 meters again. That would be a change in height. So once you do have that, you will end up changing the gravitational potential energy. So we have gravitational potential energy equal to mgh. But if you change the height, you end up changing the gravitational potential energy. So just keep that in mind when you're working these problems. All right, let's try some practice. So what is the change of GPE for a 5 kilogram object, which is raised from the floor to a final height of 2 meters above the floor? Okay, so the correct answer is 98 joules, which is answer C. For this, you're just putting in the information. So we have our gravitational potential energy equals mg, change in h in this case. So 5 kilograms times the 9.8 meters per second squared for gravity times 2 meters equals 98 joules. As an object falls downward, its GPE always the answer would be B, decreases. So if you increase the height, you can think of it like a directly proportional relationship. We have our GPE equal to mgh. If you increase any of these values, you're going to increase gravitational potential energy. If you decrease any of these values, you'll decrease gravitational potential energy. What is the change of GPE for an 8 kilogram object, which is lowered from an initial height of 2 meters above the floor to a final height of 1.5 meters above the floor? So the answer is B, negative 39 joules. So taking a closer look, we have our equation here. Now we have change in height is going to be the change, it is going to be the final height minus the initial height right there. What you get when you subtract that is negative 0.5 meters. Remember, this is a displacement. So the negative symbol here is, noting the direction, which is downward. So the gravitational potential energy, or the change in it, will be the 8 kilograms times 9.8 meters per second squared times the negative 0.5 meter change in height, giving you a negative 39.2 joules of gravitational potential energy. What is the change in GPE for a 10 kilogram object which is raised from an initial height of 1 meter above the floor to a final height of 10 meters above the floor? The correct answer here is 882 joules. So from the equation, the change in height, the final minus initial, you end up with 9 meters. Multiply all the values that are given, and you get 882 joules. Answer D. What is the change in height of a 2 kilogram object which gained 16 joules of GPE? So for this one, just rearrange the equation like we've been doing. You're going to want to divide by mg on both sides, giving you an equation for change in height is equal to GPE divided by mg. You're given 16 joules for GPE divided by the 2 kilograms times 9.8 meters per second squared gives you 0.82 meters. So answer A is correct. What is the change in height of a 5 kilogram object which lost 20 joules of gravitational potential energy? For this one, the correct answer is 4.08 meters. Just rounding it to 4.1 would give you answer A. So again, you just rearrange the equation to solve for change in height, which gives you a change in height of 4.1 meters. The practice problems that go along with this lesson include chapter problems numbers 12 to 24 and the multiple choice problems numbers 1 to 15, which you can find on Google Classroom.